Okay, so now we're going to go into our discussion of action potentials. And again, just to keep in mind what we're talking about, we've talked about the neuron at rest. We've talked about what happens initially when a stimulus comes in. It causes a graded potential. And then if that stimulus is strong enough, we get what's called an action potential. And an action potential is the electrical signal that will travel down the entire length of the axon. And this is what, if this neuron is out in the periphery of your body, out, in your tips of your fingers, and you get cut there, that electrical signal is what sends that information all the way up to your brain. So you can then do something about the stimulus that you just felt. Okay, so let's go through I'm going to show you a few different ways of viewing the action potential, and hopefully one of these ways will be something that works for you. So first, what I'm going to do is I'm going to show you again an animation of the action potential. Okay, so let me show you first. We're going to start with the nerve at rest. Imagine the plasma membrane running where the blue line is here. Here the line is orange. But this blue line, imagine that is where the plasma membrane is. On this side is outside of the cell. On this side is inside of the cell. Okay, so we're starting at rest, and we're going to do a graded potential that is then strong enough to trigger an action potential. You should notice a few different things. One, sodium is high concentration on the outside of the cell. Potassium is a high concentration on the inside of the cell. The outside is positive, the inside is negative, and how negative? Well, it's minus 70 millivolts. Okay, we've got three different proteins here. Okay, we've got the chemical gated sodium channel, which we've seen before, the voltage gated sodium channel, the voltage gated potassium channel, and the sodium potassium pump. And so these are our players that are here on the stage. Initially, these three channels, all of the gates are closed. Okay, so let's begin. You cut your hand releases a neurotransmitter, and that neurotransmitter comes and binds to the chemical gated sodium channel. Once it binds it, and here it's showing it binding it in red, the channel opens, and you noticed a little bit of sodium came in. This sodium will raise the transmembrane potential, and if that stimulus is strong enough, it will raise the membrane potential to minus 60 millivolts. At minus 60, that triggers one of the gates on this channel to open. And when it opens, a rush of sodium comes into the cell. We've brought more positive charges inside, so that will raise the transmembrane potential even more. It raises it from minus 60 up to positive 30. Now I should say, as soon as this channel opens, action potential has started. So the minute this opens, we've moved into action potential. At positive 30, a couple of things happen. One, this second gate on the voltage-gated sodium channel closes. Something else that happened is over here you notice that because we went from -60 to +30, the charge on our membrane flipped. We are now more positive inside than we are outside. Another thing that happens is that once you reach +30, you have triggered the voltage-gated potassium channel to open, and notice that allows potassium to rush out of the cell. When potassium rushes out of the cell, we've lost positive charges, which means this number now goes down. It will go down all the way to -90. As it's going down, this channel over here resets, and then eventually you get to -90. At -90, this gate closes, and you noticed we were at a +30, but now we're at -90, so the charge across the membrane here has flipped. We were positive inside, now we're back to negative. So at this point, these two channels are closed, but the sodium and the potassium are not on the correct side of the membrane. And so this is where the pump comes in. The pump will take sodium and potassium and put them back on the correct side of the membrane. And when that happens, the transmembrane potential goes back to its resting value of -70. Okay? Okay, so if you're following along with the hands-on learning activity, I just want to remind you we'll go through graded potential again, and then we'll move into action potential. So again, we would start at -70, sodium high on outside, potassium high on inside, all of our channels closed. Okay? So a stimulus happens, which releases neurotransmitter. It will come and bind to the chemical gated sodium channel and opens it. When this channel opens, a little bit of sodium can rush in, and that's going to bring our membrane potential closer to -60. If the stimulus is strong enough, meaning enough sodium is brought into the cell, we will reach -60. We will no longer be closer to, we will be at -60. At -60, we will now trigger an action potential. That happens, first, the voltage-gated sodium channel opens. You notice here, both gates are open. And so sodium, all of it, well, technically not all of it, but a big rush of sodium will come into the cell. We brought positive charges inside, so we're no longer at -60. We are now at +30. Because the inside is now positive, the potential on our membrane has flipped. So we used to be negative on the inside, but now we're negative on the outside and positive on the inside. At +30, a couple of things are going to happen. One, this bottom gate called the inactivation gate, will close. That prevents any more sodium from rushing into the cell. At positive 30, our voltage-gated potassium channel will now open, and now potassium can rush out of the cell. This will start to lower this membrane potential closer to a negative value. And as it does, the inactivation gate will open, but the activation gate will close. So this channel remains closed, but it just resets to its original position. Potassium continues to rush out of the cell, and we eventually reach a value of minus 90 millivolts. At minus 90, a couple things happen. One, we were positive on the inside of the cell. Now we're positive on the outside and negative on the inside. The other thing that happens is that this potassium channel will now close at minus 90. So now our voltage-gated channels are closed, but we still are not back at resting. Our membrane potential isn't back to the original value, and our ions are not on the side they started on. So now we have to reset these ions. What does that? The sodium-potassium exchange pump. And so it will actively pump sodium to the outside, and it will pump potassium to the inside. As it does that, it will then raise this value back to its resting value of minus 70. Okay, so what I'd like to do now is to discuss the action potential once again, but in a different format. So you need to understand this graphical representation of action potential here. One thing you should notice, again, anytime we look at a graph, the first thing you look for is the x-axis. And the x-axis is this horizontal line. And you notice its label, time. So what that means is that as time is moving forward, then we move along the x-axis in this way. This line over here is going to be voltage or membrane potential. So you may see some numbers you recognize, minus 70, minus 60, positive 30. Okay, so as we move up this way, we're getting more and more positive. As we move down, we are getting more and more negative. So let's go through this graph together. And if you're following along on your notes packet, there's a place for you to label this graph right here. While I'm here, I'd also point out that this gives you a place to write out the events of the action potential. And I would get to the point where you can write out those events completely by memory. Okay, so back to this graph. So we start out at minus 70, which means we're at rest. Okay, we've seen this number before. Now right here you start to see the membrane potential rises. So what that means is this place is where the chemical gated channels, sodium channels, have started to open. and sodium is starting to rush into the cell. So this right here would be a graded potential. Now, at some point we reach minus 60. And this is what we call threshold. That means that threshold is the value at which action potential will happen. And once you've started an action potential, it has to go through the whole process until the end. You can't stop it once you've started. Graded potentials, you can stop it as long as you haven't reached threshold. But once you've reached threshold, you've opened the voltage-gated sodium channel. And here, sodium is rushing into the cell, and our voltage is becoming more and more positive. We call this movement from resting all the way up to a more positive value depolarization. Now at this location, this is where the sodium channel, voltage-gated sodium channel closes, the voltage-gated potassium channel opens, and now potassium is rushing out of the cell. So, this stage where you were positive and now you're moving back toward resting is called repolarization. Now we notice that we actually get more negative than resting. We go all the way down to minus 90. And so this phase is called hyperpolarization. We get even more negative than the resting potential. Okay. So as you're looking at this graph, you need to know these vocabulary words. You also need to know which ions are moving into or out of the cell at each location on the graph. And you should also know which channels are open and which are closed at each point in the graph. And then you notice back here at the end, we come back to resting potential. Now, a couple of things that I want to point out while we are at this graph is that you may have noticed that how does that chemical gate that opened up here, when does it close? Well, it closes when neurotransmitter stops binding. And so as long as there's a strong stimulus making neurotransmitter, that chemical gate may stay open. And so if it's still open, it can still allow sodium in after it's reset here, and we can go through this process all over again. Now the question becomes, how quickly can you trigger another action potential on the same cell? And the answer is, it depends on this right here. This location at about minus 40 is when that voltage-gated sodium channel resets. So until it resets, you cannot trigger another action potential. And so that is called the absolute refractory period. You cannot trigger another action potential. Okay? But if we go back to look at this graph, after it's reset, that one channel, you can trigger another action potential, but our other channel isn't reset. The ions aren't back to their resting locations. So you can trigger another action potential from here over to here, but only with a stronger than normal stimulus. So that period is called the relative refractory period. You can trigger another action potential, but only with a stronger than normal stimulus. Okay. And so you can think of that as maybe the difference between a really deep cut might trigger that action potential over and over again in very quick succession prior to reset of the channels. Whereas somebody just coming up, tap, 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 that may be a more normal action potential where you get all the way to resting before the next action potential is triggered. Okay, and finally what I'd like to do is to go back to the notes packet here and fill in some information about each of these channels, just so you really understand their properties. Okay, so let's think about the chemical gated sodium channel. That's the one that's important for the graded potentials. And just if this helps trigger your memory, we're talking about this channel right here. Okay. All right. So we already filled in this information here, but which way will the ions move into or out of the cell? Well, it lets ions into the cell. Okay. How does the channel change the membrane potential when it opens? Well, it changes it from, goes from minus 70 millivolts closer to minus 60 millivolts. And where is the channel located on a neuron? We discussed this in the graded potential section, and it is going to be located in a neuron. It is located in the cell body and the axon hillock area. Okay. Now let's move down. These are the major players of the action potential. So, voltage-gated sodium channel. It moves ions into the cell. Let's make sure we have a specific here. We said that voltage triggers it to open, but let's make sure we understand that once voltage reaches minus 60 millivolts, that's what causes it to open. On the other hand, what causes it to close? That's when we reach up to plus 30 millivolts. And when this changes, how does it change the membrane potential when it opens? Well, the cell goes from minus 60 millivolts to positive 30 millivolts. And where is the channel located on the neuron? Well, ask yourself, where does the action potential happen on the neuron? It happens along the axon. Okay, voltage-gated potassium channel. Ions, in this case, they're moving out of the cell. And so what triggers this to open? Well, it opens at positive 30 millivolts, and it will fully close at minus 90 millivolts. When it opens, how does it change the membrane potential? Well, the cell goes from positive 30 millivolts to minus 90 millivolts. And I'm going to ask you to fill this in. Where do you think this channel is located on a neuron? Ask yourself again, where does action potential happen? That's where the channel is located, because this channel is important in action potential. Okay, So which ions are transported through the pump? Okay, well, we're going to have sodium and also potassium. But the pump transports them in the opposite direction. So sodium is out of the cell and potassium is into the cell. This is not applicable because the pump is always slowly pumping. So we really only see its action when these things are closed, because it's a slow pump in comparison to these channels which let a rush of ions in. But it is always there, slowly pumping. If we're thinking about the action potential, what this pump does is it's the thing that helps bring that membrane potential from -90 up to rest, which is going to be -70 millivolts. Okay, and this channel is located all over the neuron. Okay, let's look at other parts. This right here says during the action potential, the charge on the inside of the membrane changes twice. Okay, when the sodium ion moves, that causes the change the first time. We go from a negative inside to a positive inside. And then the potassium ion, when it moves, it changes the charge on the membrane a second time. We go from positive inside to negative outside. Okay. All right, and then that asks you, when do the gates on the voltage-gated sodium channel reset? We discussed that just a couple of minutes ago, so review that if you need some help remembering that. And why is this important? Well, you can't get an action potential until you reset those gates. Okay, and so that is action potential. I would recommend that you go over and over this again, and then your group project helps you think through what are the consequences if the action potential is not working properly. This is probably one of the more difficult concepts of the course. It's molecular, it's abstract. You can absolutely do it, and you must know it, but get help. Ask for clarification. Ask to know if your understanding is correct, or ask for it to be explained again. But take charge of your own learning and make sure you know this concept.